Good evening, everyone. Welcome back to another tutorial. Uh, I have been working a lot on a tutorial world, so I could try and better teach people about the game, because there's a lot of different mechanics in the game, and a lot of different functions in the game. So I have a lot of work left to do, but I figured I could get the basics and routing out of the way today, because routing is the most requested feature of the tutorial world, and it's honestly not that bad. I've already gotten the world set up for it. Let's get into it. So in this tutorial world, there's an index here. So floor 0 is where we're currently at. This is where the index lives. Floor 1, recycling, and then 2 and 3 are what we're focusing on today. It's a nice typo. Let me fix that real quick. So let's go on to floor 2. The save is available in the Discord under the saves channel. I'm just going to kind of run through these just so you can get an idea of what we're talking about today. So packets inside of the tower networking game, there's two different types, just in a general way of speaking. There's broadcast packets. It's basically somebody yelling out into a crowd, trying to find somebody that will accept the packet and do what they need to do with it. So, as an example, a phone on your network is broadcasting its traffic. It's screaming out, looking for someone to accept that packet and convert it into a VoIP phone call. On the flip side, we have destination packets. Destination packets are packets that have a specific destination that they are targeting. So let's say I need to reach this debugger here. If we look at this debugger, it has a network address and it also has a hardware address. If I say ping 84527, it's going to send a ping looking for that address. If I do ping at address debug, it'll send a ping looking for that specific address. So the two different types, the untargeted and targeted. Network addresses in the game are what we were just talking about. So we have two different types of addresses in the game. We have the hardware address, which is a string of up to 5 numbers, fully randomized, and it stays the same for that device through the entire playthrough until you get rid of the device. You can use this as a form of address. You can route to it, you can ping it, you can send commands to it, but it doesn't take advantage of a lot of the things that you really want to do in the game. So this is why we have network addresses. This lets you change a string of numbers into a actual address. So where it says network adder, that is a string of characters that I set to help me define what that device is. This lets us create routes. It lets us see what that device is, and it lets us actually have some sort of mental idea what's on our network. In the game, we have two different types of network addresses. I'm not reading word for word. You can read. I trust everybody here can read. But we have two different kinds of addressing when it comes to the network address. We have a static address, and those are addresses that are on the device, survives the reboots, and basically never changes. In order to make that happen, you need to make sure DHCP is disabled on that device. Otherwise, if you reboot it, it's going to go try and pull an address from DHCP. We'll get into DHCP later. But basically, in order for a network address to stay, you must disable DHCP. If you are doing a new game, if you go under advanced difficulty settings, there are two settings in there for DHCP. There is my devices, or the player's devices, and then there's customers' devices. I personally always set the my devices to disabled so that all of my addresses are static. I personally have no reason to do DHCP on my own devices. When it comes to customer devices, though, I turn it to on boot because I really don't need them checking in that much. But again, we'll get into DHCP later. The other one is dynamic network addresses. Dynamic addresses come from DHCP. Basically, you send a request out. It says, hey, I need an address. And then DHCP gives you an address. That could be different every reboot. It could be the same. It will most likely be different in the game's case. Moving on. So in the game, what we think of as like a link speed for real world stuff is traversals and bandwidth in the game. So every time a packet hits a port on a device, so the inbound traffic, it counts as a traversal. Any traffic hitting an inbound port. So any of these ports on the switch, if a packet hits it, that is a traversal. That was the inbound ingest of that packet. If this port over here gets a packet and this port gets a packet, that'll count as two traversals because it's two inbound packets. So each device has a non-infinite amount. So if we open our mobile OS and we go to Netshell, and then we do always using this debugger, if I type watch and the device's address, you'll see that we'll start getting a packet going outbound. If we look over here, this network load, it's going to keep staying down at 0 because the polling rate of this is slow enough that you won't notice it. But this network load up here is the maximum amount of input packets this device can handle per tick. So a tick is just how often the packet simulation actually runs. So for these devices, if you send more than 28 packets at this device within a tick, it will start dropping packets and it'll overload. We don't want that. If I do watch on this blade, you'll see that this one has a different network load. This is 25, the server was 28. So this basically shows that each device in the game has a different amount of bandwidth that it can accept in the form of traversals. So we want to balance our network so that we're not overloading specific devices. I'm going to just type a random thing to cancel this. I'm going to close that. In this game, there are no response packets. In real life, we have DNS lookups where I send a request to a DNS server and then it sends a packet back with the information that I need. That doesn't exist in the game. If you send a DNS request, it'll hit the DNS server and then you will magically have that information. You don't need anything going back for DNS requests. There are very few exceptions. We have Decentro, which is the cryptocurrency that we'll talk about later. And we have certain other Tenable specific programs that we'll get into later. But in general, there's really not a lot in the game that is a two-way communication. There's really almost nothing. So in the world of the game, you really only need traffic to flow one direction in order for things to work. So let's say you have a floor of 3 users. Those 3 users, besides if one of them is a Decentro user, we're ignoring that. For simplicity's sake, we just have 3 standard users on a floor. They only need to reach your DNS server and the host they're trying to reach. So those 3 people, they want to reach DNS and they want to reach, let's say, the recycling floor. As long as they can reach those one direction, they don't care that anybody can reach back to them. So I, as the administrator, do not need to set it up that all floors are routable. I can just leave them on their own to do whatever they want, and it doesn't matter. That's just a nice thing so that we don't have to manage even more endpoints than we need. Moving on over to traffic types. Every single packet in the game has a type. So if we come back over to here, remember how those were blue packets that were traveling? In the game, you can do always color, and that allows you to actually color your packets, which is super cool. So those blue packets that I was sending are TCP23 packets. And TCP23 is what our debugger uses. It is a one-way communication. Like I said, ignore the TCP. But it sends that packet out. You see it get consumed by the device, and then the data comes back to me immediately in a magical way. So every single traffic has its own port number and its own type. There are certain things that mesh together. So like there are certain store text requests that use the same port. There are certain different pieces of traffic that use the same port number, but it still has a traffic type associated with it. There are unofficial docs made by Avril that you can find on the Discord that lists every single traffic type in the game. And there's other methods to actually find those traffic types, like doing PCAPs in the game. You can do watch and see the actual packets that are coming into a device. So if we do watch on this device again, you see how it says hit tab key to cycle different views? You can actually cycle to the port view, and you can see I've received 127 packets. Top is TCP23 to this device, because I'm sending it TCP23 packets all the time while I'm doing the watch commands. Moving on over. So usage. Going back to watch the other server that's here. So on this server that's over here in the corner that we showed earlier, we have a couple of different things. So I've installed a program on this server over here. It is running, and if you look down here, we have a usage stack. This usage stack is store text and store image. What this means is these services are available on this device. So let's say one of our other programs required store text and store image. That program is going to send out a request looking for store text and store image. And once it gets a packet to this device, it'll drop this count down by 1. Or if the machine needs 2, it'll drop it down by 2. And that is the usage on a device. So usage is entirely based on what you are trying to do. We have producers, which produce usage. So Padu v1 produces store text and store image. It doesn't take any inputs. It just produces. Next we have converters. Converters are devices that take a certain usage in and put another usage out. A good example of this would be VoIP phones. The VoIP server program describe VoIP server. Bad example. This program actually accepts VoIP phone connection. This just needs to be fixed. It accepts a VoIP phone connection in. So a phone produces accept VoIP phone connection and outputs it onto the network. This server then accepts that usage and outputs converting the accept VoIP phone connection into stream voice. That is the entire point of this program. If I do this instead, hopefully this one's correct. Nope, that one does the same thing. Mailer. Don't have it unlocked. get to coffee. All right, so program type converter. So required inputs to store text. So if we remember earlier, the Padu that I was doing was producing to store text. So get coffee would request those to store texts from Padu, and it would output 16 read text, 16 update software per tick. So we would have both of these stacks available as usage. That's what a converter does. So the third type is just a consumer. Basically, consumers just send a packet. This is like a user. Get Coffee is a consumer. Get Coffee sends a request for store text out to the network, and it consumes that usage. Those are the three types. So that's a majority of the basics of the game. Let's head on up to routing. Routing is a doozy. Do not let it scare you. Once you actually understand the concept, it's pretty simple to actually implement it. So we have different types of routers. These are quote-unquote core routers. These have very high bandwidth, but they are only fiber optic. Down here, these are the HA routers. These have the ability to duplicate traffic between ports. That's why it says HA support on these. And then this one's just the color. There's standard routers. I don't think I have a shelf for those. And then we have the VLAN capable routers, the kilos. These ones handle VLAN routing. Only specific routers handle that. We'll talk about that at some other point. So, routing is it's basically what I call one of the cornerstones, or maybe even the foundation of the game. You need to learn it. You don't have to use it, but it'll make your time in the game way more enjoyable. So routing allows you to take a packet in to a port. So let's say a packet comes in on 0, and it lets me basically assign it some rules. So let's say a packet comes in and it's UDP 5060. That is phone traffic. That is a port that I need to send to a specific location. I need to send that to my VoIP server. My VoIP server is plugged in on port 1 here. So I'll make a rule on this router, basically a gate. I like to use an airport as a analogy here. I walk in to security. I need to go to a specific gate. So I have a ticket for the gate that matches UDP 5060. And if I have a route to this gate, I'll come out this port. If I don't have a matching ticket, say it's to a UDP 5080, UDP 5080 doesn't exist in the routing table, so I'll go out the default exit port. I didn't have a valid ticket. I wasn't allowed through security, so I was just sent out the exit. So that's basically routing. There's a lot more that we're going to get into. But if nothing matches, it goes the default route. If something matches or partially matches, it goes out the prefix route. That's that. In the game, there is a proposal that kind of makes routing easier. RIP. It requires you to have 8 routers, and then you have to unlock it via Secretariat. But RIP is Routing Information Protocol. It allows routers to share their route tables across each other. So in this example, these I'll kind of read. We have D1 over here. D1 has D1 SR1 attached to it. And basically inside of D1, we've said, hey, D1 SR1 lives on port 2 of D1. So D1 knows that it exists, and it'll advertise that route to D1SR1 over the network. So D6 now knows, oh, D1 owns D1SR1. If I have any requests for DR1 or D1SR1, I need to send that packet over to D1 so D1 can route it. And then it takes that same knowledge and it sends it along the line to D9. D9 now knows, oh, D1SR1 lives down this route because D6 says it knows how to get there. So D9 will now send requests to D6, and then D6 will send it to D1, and D1 will make the final connection. If D1SR1 wants to make it to D9SR1, it will make it the exact same direction. D9 will advertise to D6, D6 will advertise to D1, D1 will know, hey, I have a packet for this location, I need to go here. This only works if you set the endpoints of the addresses. It's not like a automated discovery thing. That's not what it does. You still have to set it up. If you set it up wrong, it will still break. So, in this instance, D1 had to be told that it has D1 SR1 access on one port, and it had to be told that it had D6 access on another port. Just like D6 had to be told it had access to D9 and D1. Really, you only need to set up the D1 and the D9, and then D6 will just pick it up from there. But you're already setting up the routes, right? You can set it up so that RIP only advertises on specific ports. So in order to save bandwidth, you really don't want to send packets at devices that you don't need them to go to. So D1, for example, I don't want to advertise to D1SR1 because it doesn't understand routing whatsoever. So instead, we'll do RIP advertise via port 2 on D1, and port 2 is what connects to D6. It will now only send its advertisements on port 2. RIP listen is what churns it on and off. So if you do RIP listen on, it will churn on the listening for if D6 wants to send it routes. This is where we get into the meat and potatoes of the game, and kind of the, I don't want to call it complicated, but this is the fundamental that you need to understand about the game. Prefix routing. So, what prefix routing is a way for devices to kind of assume where traffic belongs. So let's say we're working on this user here. This user wants to reach D4 SRV1. Their packet reaches D4, and D4 knows that it owns this server, so the packet travels perfectly fine. However, these users actually want to access D9 SRV1. So the packet reaches D4, and D4 is like, what in the heck is this packet? I have no idea who owns D9 SRV1 because it's not in my routing table. So what it's going to do is it's going to actually take this name. Oops. I'm trying to make a new one here for you guys. So at D9 SRV1. So it's going to take this name, right? And it's going to take one letter off the end. It's going to look at its routing table, and it's going to find, oh, I still don't have a match. Nothing is similar to D9 SRV. It'll do the same thing again. Oh, I still don't have anything. Take one more off. I still don't have anything. One more. Nope. One more. And oh, wait. I do know where at D9 is. So it sends the packet over to D9. Once it reaches D9, the process starts over again. I am now at D9 SRV1 again. Oh, D9 knows exactly where it is. Let me finish the packet. That's all it is. It is just a way for routers to figure out where to send packets. And that's all it is. It removes a letter at a time from the end of a word until it finds a match. So even if, let's say we did D6. If this packet made it here, it would go down to at D, and then it has no idea where to send this. This is going to be a dead packet. This is just the fundamental of how this works. It'll send it most likely one way or the other, because both of these are matches. But either way, this packet is now a dead packet, because it has no idea where that link is. That's prefix routing. So in the part 2, we now have 4 different data centers. These different data centers are 3, 6, 9, and 12. This one might be a little harder to show. So at D15, or no. Let's say I need to reach at D12 SR1. And I'm over here. This is going to be a little bit more difficult, because if we follow the same idea, this will fail, because we start removing characters, we get all the way to D1. D1 doesn't exist. It doesn't know. So there's 2 things that you may need to do. Either you change your prefixes, or the easier method is to just add the routes. So each core knows where the other cores are. That's the way I do it. It's the simplest way to do it, and it's just easy. So what we would do is we would do a route add D6 via port 1 on D3, and now D3 knows how to get to D6. So it'll send that packet to D6, no problem. Now it knows how to get there, right? However, we still don't know how to get to D9. So now we do a route add via port 1 at D9. So now this knows, hey, D3 or at D9 takes the same path. So send it to D6. D6 will know how to route it. And then D6 has the route to the proper port of D9. So D3 sent it to D6. D6 is going to send it to D9. Again, same thing. You need to add via port 1 at D12. So now D3 can get to this one, can get to this one, can get to this one. This is where RIP is good, is for talking about these cores. In actuality, the amount of data centers you have is probably going to be very low. I usually do about 15 floors per data center. So your tower will get massive before you need to make this many data centers. It really depends on, obviously, your playstyle, I should say. But in the long run, if you really needed to have 8 data centers to cover 120 floors, adding those 8 routes to the routers probably isn't a big deal. But again, this is where RIP comes into play. RIP would send all of those addresses to each of the routers on the core level, so that you don't use it on the lower levels, because it's not really necessary. Let's go ahead and delete that. Hopefully that makes sense, because as long as you understand prefix routing, you're pretty much able to do anything you need to in the game to actually deploy stuff. So let's do an example run real quick. So in the game, if you didn't know, if you open the monitor, you can middle click on it to slide it left and right. So let's go ahead and work on this tutorial together. RIP is simple. We're going to go ahead and select this debugger. So if you right click on these devices, you can get the network address of the device. You see it's in red. If you hold Control and right-click, you get the blue one, which is the hardware address. Either one works right now, so we're going to do always using. And now we're going to be coming out of this debugger. So in this, these are not named yet. So let's go ahead and do that. Net address set at D1 on. Go ahead and copy that. Now this device has a address. So we have at D1. Now we need to do net address set at D1 SR1 on this guy. Oops. Now, if you noticed, that packet went up to D1 and then magically made its way down to the other router. And why that is, route show on. You know how I was talking about those gates? This device has no idea how to get to this router. We have no routes inside of here. But unmatched traffic defaulted via port 0. So that packet had a ticket to reach 38335. There's no routes. So what it did is it sent it out the default port. And that allowed it to reach down here. So now both of these devices are named. And we can go ahead and enable RIP. So RIP advertise via port 0 on this guy. So this router, as you can see, is now sending a packet out every once in a while. That is its RIP advertisement. Obviously, this server or this router isn't listening for it, so it's not doing anything. I'm going to go ahead and do RIP advertise on D1. And I'm not going to care to specify a port. I want this one only advertising on port 0 so that I don't overload my server. But this one is my core router. My core should be able to figure out who's where. So as you can see across this link, there's another router over here. Eventually, that's going to communicate. Next up, we need to actually turn it on. So rip listen on D1 and rip listen on D1 SR1. So now both of these are listening to each other. So if we do route show on D1 SR1, you could see these have found each other all of a sudden. They now know who the other person is. In our routing tables, an orange number here on the left is actually a ripped found device. So because we're listening, the devices have found each other. And that's exactly what we want. So if you notice though, route show on D1, that's only D1 SR1. Same with DRSR1. There's nothing here other than D1, which means we can't reach this server. So if I try to ping this server, it sent that packet out, but it's going to time out because I have no idea how to get to that device via my gates. So what we need to do is route add the server name. You can also do the ID, but IDs are not routable in the general sense. You can set it up so that 27788 has a ticket on this port. And because we're using the default port, that'll make it down here. But you'd have to set up that route across the board. It's just not good practice to route based on numbers. So route add that device via port 4. This is P4 on the device. So now if we do route show, you'll see we now have a green number. This is a statically set route. This is one that I set up, right? And then if I try to ping it now, this went up, went out the default, and it went to my destination. If I do route show on this guy now, You can see I now have another orange number in here to that device. It knows, hey, Mr. SR1 owns that device, so send it out port 0 and SR1 will take care of it from there. That's RIP. So, moving on over to the standard routing principles. So, I'm going to switch to buggers. So, always using this guy. If I do route show on this guy, you can see RIP's already enabled on this guy. So, I am listening for traffic on this one. So, I can ping from here this device. As you can see, it took the proper route and went all the way over there. This is why a lot of people like route, because it automatically sends that routing information along the line. I'm going to disable RIP on this one. I forgot the command. Hold on. Command RIP. RIP stop. Ignore. RIP ignore is how you stop it. So it's no longer listening for route advertisements. So if I go route show on again, you can see it's now dark. If I tried to do that ping again, it's going to fail. It's going to send it down to this router. So now we're not listening anymore, but I want to show you how the prefix routing works. So let's go ahead and follow our example here. I'm going to move my monitor back over. And the principles are really shown here. So this is a user broadcasting packets, right? So you can see there's a bunch of broadcasts looking for DNS. It's coming into here, and it's following this port 0. I can change this. So route default via port. Let's send it back on itself because we're crazy. You can see now it doesn't actually send it back on itself. It's now dead. And then I can change it to port 1. And now that traffic's heading over there. And then it's heading down the default route. So it's just like an exit gate. If you don't have a matching ticket, you're going out that default. However, these are broadcasts. You can disable broadcasts. So route route. Even with all my time, I still have to read the manual every once in a while. So route disable drop broadcast. And now you can see broadcasts aren't even getting through here. If we instead do route add traffic UDP 53, which is DNS, via port 0 on the router, you can see it still doesn't get through. It is blocked. We are killing broadcasts outright. So I'm going to re-enable broadcasts. And now you can see the packets are flowing again. If we do a route show on this guy again, you can see our default is port 1. But those packets aren't going out port 1 anymore. They're coming out port 0 because we added a traffic route via port 0. So you can control where this traffic goes basically anywhere. You can send it out any of these ports. You could drop it out port 9 if you want, which is a dead port, so the package just dies. You can do a lot of things. It's up to your imagination with what you can do in this scenario. So that's broadcast, and that's traffic. So in later tutorials when we're setting up like VoIP, or if we're setting up cameras, you want to be able to add route traffic to set up the way for the phone traffic, the camera traffic, DHCP traffic to reach its endpoint. And that's how you do that. Route, add traffic, the port number. Let's do 67 for DNS via, or not DNS, DHCP, sorry. 1 on the device. That's the syntax. Very important syntax, one of the most used syntax you're going to use. Okay? Let's go back to the other setup. So, in this example, I'm going to set this up to communicate. So, per my board here, we're going to do route, or net address set at D3 on this guy. So this is now at D3. We're getting flooded with DNS packets. So we're routing them via 0. We can disable, like I showed you, but it doesn't really matter for this tutorial. We're now also going to do net address set at D3 SR1 on this guy. Oop. I changed the default port. Route default via port 0. And this is how the default routes can mess with you. So now we have SR1 down here. We want to look at this. So this server is DNS. So let's do a route show on our new server router. We have no routes. So if I want to reach this server, I can't. So route add the server name via port 2 on this guy. Nope, on this guy. And now if we try to ping again, that ping will get through. So we're getting DNS packets on port 1. If we do a watch command on this guy, you'll see that this guy has 20 reply DNS queries. These DNS requests are making it in, but they're dropping. So we need to do route add traffic UDP 53 via port 2 on this guy. Now you can see all the packets are making it through, and we have overloaded this server. We need to add another server on. Not going to do that in this tutorial, but you could see that the packets are now making it down there. Now, I'm going to go ahead and turn this off because I don't want the packets to come through. As you can see, my packets are still making their way down there just fine. If I try to ping this server, you could see that it just took the default route. It didn't work. So we do a route show on this router. It's only got UDP 53. I have failed myself. I need to add this guy so that it knows where to send destination packets. It'll obviously use the default port, but you should make a habit of having the defined routes on your routers. Okay? So we need to add this data center D1 to this thing. So route add D1 via port 1 on this guy. Now watch. It reached it. Just by me telling it. Oops. Just by me telling it where to find D1, it made it all the way over, and then D1 figured it out from there. That's prefix routing. I don't have to tell it anything. I can reach everything on that side of the network. I don't know if it knows how to reach this debugger because I don't have a route for it. It doesn't. It's also not in the prefix, so this wouldn't route anyways. But that's prefix routing. That's routing. Routing is very simple. Putting it into practice is the challenge, and making it work in your mind and making it work in a way that is scalable is the learning experience of the game. It's the learning experience of really network engineering in general is making things scalable and not overcomplicating things. So, if you have any questions, feel free to ask in the Discord. Feel free to drop a comment. Any support is appreciated as always. Have a great day.